All right, you gotta see this. I've been digging into a brand new research paper from Google, and it is, well, it's out there. They're seriously proposing we take the massive data centers that power all our AI and launch them into space. And no, this isn't some sci fi movie plot. This is a real engineering proposal, a moonshot idea, aimed at solving one of AI's absolute biggest, dirtiest secrets. I mean, we see it every day, right? AI is doing incredible things, writing code, discovering new drugs, you name it. It feels like its potential is just limitless, expanding at this breakneck speed. But there's a catch. There's this huge hidden problem lurking behind all that progress, a fundamental cost that we're really only just starting to wake up to. And here it is. AI is unbelievably thirsty for energy. We're talking a shocking amount. The explosion of these super powerful models, like transformers, has kicked off this parallel explosion in how much power they need. These systems are just guzzling electricity, and our data centers here on the ground are seriously struggling to keep up. The bottom line is, the bigger AI's role in our world gets, the bigger its environmental footprint becomes. So let's really dig into the scale of this problem, because to get why this whole space idea isn't completely crazy, you have to understand what AI is becoming. The authors of the paper frame it as more than just a tool. They see it as something way, way bigger. Think about it like this. They're calling AI the next general-purpose technology. Just like the steam engine or electricity, it's something that's poised to change, well, everything. And just like we had to build a massive global power grid for the age of electricity, the paper argues we're going to need a whole new kind of infrastructure for the age of AI. Because if AI's demand for power just keeps growing exponentially, where on Earth are we going to get it all? Well, what if the answer isn't on Earth at all? That number, that is the power output of the sun. It is the biggest energy source in our solar system, and it's not even close. It's putting out trillions of times more energy than all of humanity combined. So the Google researchers asked a really simple, almost profound question. Why are we building our most power-hungry computers so far away from the ultimate power source? And that question leads us right to the heart of their moonshot idea. Instead of struggling to meet AI's insatiable energy needs down here, what if we just move the computers up there, right next to that constant, basically limitless fountain of energy? And the difference in just pure efficiency is staggering. Look at this. Down here on Earth, you've got night, you've got clouds, you've got the atmosphere filtering out a ton of sunlight. But in the right orbit, a solar panel gets a near constant, unfiltered blast of sunshine. The paper actually calculates that a single panel in space can capture up to 8 times more energy in a year than the exact same panel on the ground. 8 times. This quote from the paper just nails the paradigm shift. For decades, people have talked about space-based solar power. But the big stumbling block was always, how do we beam all that energy back down to Earth without massive losses? Google's idea just flips that completely on its head. Don't move the power to the computers, move the computers to the power. Okay, so what would one of these data centers in orbit actually look like? This is where the engineering gets really, really cool. It's not some single, giant Death Star-looking thing. It's actually something way more clever and scalable. Let's break this down. First, you've got the swarm. It's not one big satellite, but a whole constellation of smaller ones all flying together in a tight formation. Then you've got the brains. Each one of those little satellites is basically a node in a giant supercomputer, packed with Google's powerful TPU chips. The nerves of the system, what connects them all, are these ultra-high-speed laser links. And finally, there's the orbit. The whole swarm flies in a special path called a sun-synchronous orbit. It's kind of like finding the perfect sunbathing spot in space. It gives them constant 24/7 sunlight for power. And to make this a little more real, the paper actually models a starter kit version. A cluster of 81 satellites, all flying within just a 1-kilometer radius. Now, because of orbital mechanics, they can't just sit still. They're constantly performing this beautiful, intricate little dance with each other, expanding and contracting, just to keep those laser links perfectly aligned as they whip around the Earth. Okay, so this all sounds amazing in theory, but I'm sure you're thinking about all the ways this could go wrong. I mean, building anything in space is ridiculously hard, let alone a flying supercomputer. So the paper dives right into the biggest technical hurdles, and the first one is a doozy: radiation. Think about it. The super high-performance chips in our data centers are incredibly delicate. They were never designed to handle the constant bombardment of high-energy particles you get once you leave Earth's protective magnetic field. So, wouldn't they just get fried? So, this is one of the most surprising parts of the whole paper. They actually took their latest TPU chips, put them in a particle accelerator, and just blasted them to simulate years of space radiation. And the result? They worked. They survived a radiation dose equal to a 5-year mission with no permanent damage. Yeah, they had some data errors, what they call bit flips, but the rate was low enough that standard error correction software could handle it. It turns out our commercial-grade chips are way tougher than anyone thought. All right, next big hurdle, communication. For a supercomputer to work, its chips have to talk to each other incredibly fast. We're talking terabits per second. But the laser links on satellites today, they're built to span thousands of kilometers, and they max out in the gigabits. That's a performance gap of like 1,000 times. It's like trying to run a data center on an old dial-up modem. It's just not going to work. But the solution here is just beautifully simple, and it's all based on physics. See, the power of a laser signal you receive gets exponentially stronger as you get closer. So by flying the satellites in that super tight formation, just a few kilometers apart, they can use commercially available high-bandwidth optical gear. They can basically create a wireless fiber optic network right there in the vacuum of space. So we've got radiation handled, we've got networking figured out, but none of this matters if you can't solve the one problem that has killed ambitious space projects for decades, the absolutely astronomical cost of just getting stuff off the ground. This is the magic number. The paper and a lot of folks in the space industry point to a launch cost of around $200 per kilogram. That's the tipping point where building massive infrastructure in space starts to make real economic sense. But how realistic is that really? Well, this timeline shows the revolution that makes this entire paper plausible. Thanks to reusable rockets from companies like SpaceX, the cost to get to orbit has just plummeted. The paper's analysis suggests that if this trend continues, especially with next-gen vehicles like Starship coming online, we can actually hit that sub-$200 target sometime in the mid-2030s. And if that happens, what's the payoff? Well, this table lays it out pretty clearly. Right now, on Earth, a data center can spend anywhere from about $570 to $3,000 per kilowatt per year just on the power bill. The paper's calculation shows that if launch costs hit that $200 sweet spot, the cost of launching your solar panels into orbit averages out to about $810. All of a sudden, putting your data center in space isn't just feasible, it's actually economically competitive. So we've seen how Google's team is methodically knocking down the biggest barriers: the radiation, the networking, the cost. It's a really compelling vision, but they're also very clear that this is just the beginning of a very long road. And of course, there are still huge challenges left to solve. Like, how do you fix a computer chip when it's in orbit? How do you keep these incredibly powerful processors from overheating in a vacuum where there's no air? And importantly, how do you get all the useful data they create back down to us on the ground? These are the next big research questions. And this final quote from the paper really sums it all up perfectly. This isn't some final blueprint they're handing over. It's a roadmap. It's a series of difficult, but potentially achievable milestones on the path to what could be the next great leap in how we build computers. Which leaves us with a pretty mind-bending question to chew on. For the entire history of computing, our machines have been tied to the surface of the Earth. But as their hunger for energy just keeps growing, we might be reaching a point where the most logical place to build our most powerful thinking machines is out there among the stars.